morning, everyone. Welcome to this session, doctoral meeting session on our Space Science and Technology PhD program. I would like to thank you all, our 7 speakers today, and all the audience, including the supervisors, for being here. Today, we're going to be discussing, talking, and listening to the presentation of the PhD students that are working on different problems related to astrodynamics, space tethers, also space debris, GNC problems related to space, etc. Right, so it's quite interesting topic. We have also some industrial PhD thesis, some academic PhD thesis, and I hope you all enjoy. Okay, so sorry for these minutes of delay and these problems with the connections, but I think we are all here now. We're gonna start with Luca and Sadaf. They're gonna be presenting topics on space tethers, right? And then we will continue with Sergio and with the other established before. Okay.
All right. So good morning, everyone. My name is Giuseppe Di Pasquale. Today I'm going to be presenting my PhD progress. So I'm doing a PhD at UC3M it's an industrial PhD carried out at ENA Space. The title is Design of Optimal Attitude and Orbit Control Systems for Multipurpose Electrospray Micropropulsion Missions. My advisor from UC3M is Professor Manuel Sancourt-Rivo, and my supervisor from ENA Space is Dr. Daniel Perez Grande. So this is a bit of the outline of what I'm going to be presenting today. So just a very quick introduction on ENA Space, the problem motivation, the objectives of my thesis, the methodology I'm going to follow, some preliminary results, and future steps. So ENA Space, this is just to give a background for who missed my colleagues' presentations on Monday, is a startup founded by 3 UC3M PhD graduates, in particular from the EP2 research group. This is just a snapshot of the current team. ENA Space basically focuses at the moment on 2 products: Athena, which is a modular, efficient propulsion technology based on the electrospray technology, and ENA-Go, which is a mission analysis tool which focuses on the implementation of this electrospray technology. So the problem motivation, Athena is based on this building block that we call stack. A stack that you can see here, a rendering, is composed of a microfabricated chip, which basically allows to emit high-speed particles from a liquid source through the principle of electrostatic acceleration, and a reservoir which contains the liquid propellant. So the point is that these stacks can be combined in a modular way to provide different thrust levels, and also the reservoir size is variable, so you can also provide different total impulses. Additionally, you can regulate the voltage of each stack, so you can also tune the performance. This means that the thruster can be finally adapted for each mission, so there is a potentiality for optimality for potentially any prospective mission scenario. But there is an additional degree of freedom, or some additional degrees of freedom in the system operation and design. So there is a need for tools to handle the increased complexity. Another thing is that with this modular approach of the thruster, if using asymmetric operations, so as you can see in this rendering, firing only 3 of the 8 stacks, you can produce torques, therefore attitude control. With this the configuration you see in this rendering, this is a planar stack configuration. You have 2 degrees of freedom, so you can do some alleviation of loads on the spacecraft ADCS, some reaction wheel unloading. But with non-planar stack configurations, so for instance, stacks also on other faces, you could achieve also 3 degrees of freedom of control. So the thesis objective, the first one, is the development of an optimization code for the guidance of trajectories using this electrospray thruster with a focus on low Earth orbit. And the second objective, subdivided in 2, is the development of a control law, which is coupled, of course, with the guidance law obtained in the first objective, and using the electrospray as actuator. And the second part of the second objective is actually the testing of a prototype of using an hardware-in-the-loop approach. Of course, being a PhD, there's also dissemination of results, outreach, and thesis writing. At the moment, I am here because I started some months ago. So the methodology is, I think, quite standard. So starting with the literature review for the first objective, the development of the multi-objective optimal maneuver algorithm, and finally, a development of the software and the deployment of this software on a software as a service platform, which is maybe more in line with the industrial goals of ENA than academic goals, let's say. And then for the second objective, starting in a, let's say, similar way, so with literature review, development of control algorithm and software, and then going towards the experimental part, which again is maybe more industrial. Maybe so the first objective is more academic, so it's going to probably produce a paper or some papers, and the second part again is more on the industrial slope of the thing. So I'm going to show you now some preliminary results. I've been working on the development of in-house orbital mechanics and attitude dynamics code in Python, which is called ENA 360. Here you can see a structure. There is a propagation loop in which you have the dynamics and all the various perturbations that can be enabled depending on what you want to study. And then there is an outer loop that is let's say the control loop, in which you have thruster or attitude actuators that can be optimized through an optimizer, which is what I'm actually working for the PhD basically. So the optimizer strategy for the first goal is basically based on the Q law. Now the Q law is a way of producing solving the problem of let's say of multi-revolution trajectory optimization using electric propulsion that does not require the solution of NLP. It can be easily embedded in a propagator, so it's very fast and it allows to achieve anyways near optimal solutions. And additionally, there is also already UC3M heritage on this type of guidance law from the thesis of David Morante. So what I've been doing in this regard is the implementation of this Q law in perturbed environments. So considering, for instance, the J2 harmonics, the atmospheric drag. And so one thing that I've been trying to do is actually to embed the J2 perturbation in the formulation of the Q law, which actually proved to be, proved to have poor performance. Another thing that I've been doing is experimenting with, for instance, feeding Brouwer-Liden transformed orbital elements as input to the Q law. And this actually was good because it allows to adjust for the stopping condition problem that you have when you include the J2 perturbation, so the oscillation, the short-term oscillations. And additionally, it also proved to outperform in some combined cases. So if changing several elements at the same time by feeding these averaged values to the Q law, it actually gives better results than actually feeding it the oscillating elements. So another thing I've been working on is a development of an optimal run spacing strategy, which is based on the Q law coupled with a genetic algorithm, an SGA2. This strategy is basically an indirect maneuver. So there's a first phase in which semi-major axis and inclination are changed in combination. And then there is a phase of costing in which the J2 perturbation actually is exploited to obtain the desired run spacing. And finally, there is a phase C that is basically going to the final target orbit. So a second maneuver. And this strategy can be used to optimize. In this strategy, we can also optimize the thruster design and the operation for each phase. So some preliminary results on this topic. You can see here a Pareto front for the mass of propellant and the time of flight for this maneuver for specific case. And what you can see is, first of all, that with this combined approach compared to only semi-major axis approach, you can achieve a much shorter duration for the maneuver. And also, you can actually see, if I zoom a bit, that the maneuver is more efficient because the genetic algorithm is basically combining also at high duration, a change in semi-major axis and inclination, which is more efficient than just changing the semi-major axis. We sent an extended abstract. We submitted it for the Spaceflight Mechanics Conference that's going to be held in January, and we'll see if it's going to be accepted. Built on this progress that I've shown you, there is the design methodology that is basically a joint optimization of the maneuver and the thruster. So in response to what I showed you at the beginning, the problem, let's say, of designing this thruster. So this design methodology is based on the rapid generation of Pareto fronts for different performance indexes, such as cost, mass, time, and for different mission scenarios. So for instance, a simple transfer or run spacing or combination of these maneuvers. It can include complex constraints such as attitude rate constraints, eclipses, and this is just an example of results that I can obtain with this methodology. You see here, I am basically finding what is the configuration of the thruster. NS equal 8 means the thruster has 8 stacks. In this case 6, in this case 4. And as you can see, there is a solution that for a given power and a given number of stacks minimizes the total cost, considering the cost of the full spacecraft and also the operation cost. And then, this methodology, we're going to be presenting it as a multi-purpose modular micropropulsion system design optimization at the Micropropulsion CubeSat conference in September. Another thing I've been up to is the benchmarking of these guidance laws, of these results against GMAT, high fidelity environment, so considering various perturbations. And you can see that there is a good, the results match quite well. So future steps, I'm going to be, first of all, improving the optimization strategies and extend to more maneuvers, such as true anomaly facing or drag compensation and so on. Then I'm going to be deploying this solver, in particular the one based on the genetic algorithm, on a cloud computing platform, which is significant for speed up and testing of the algorithm. Then I'm going to be developing a power module which allows for detailed evaluation of energy balance. So, for instance, optimal measurement of eclipse constraints, which for electric propulsion is very, very important. Another thing I'm going to be doing, again in the context of the first objective, is the investigation of variable operating point solutions. This is one first attempt. As you can see, the specific impulse and the thrust are varying over time. And you can see here, it's actually the orange point. It proves to perform just a bit better with respect to the constant operating point solution, but this is to be investigated much more. And finally, I've been developing an attitude dynamics module, first of all, for the evaluation of the attitude let's say, the impact of attitude error on the optimality of the guidance law. And second, also for the development of the attitude control laws, which is important in the context of the second objective. And here you can see just some preliminary results with a simple controller trying to follow the guidance law obtained with the QLO. So thank you for your attention. If there are any questions, I'll be very happy to reply.